Good morning. If you're on the same time zone as I am, this is Friday, and as you remember, Fridays we do labs. So we just finished lab 2, and today we're going to talk about lab 3. Remember, we were also talking about finite automata and regular expressions. This was Monday. We'll continue where we left off next Monday. Now we're taking a break from that material and jumping into the lab. Now I'm seeing, so lab 2 was due yesterday. I'm seeing quite a lot of questions on CampusWire early on, so that's good. I'm hearing from our TAs that people do show up for lab sessions, and so that seems to be going great. But I also see that there's quite a lot of requests for late submissions, all kind of mishaps with not committing things properly or not managing the time and things like this. I'm very lenient for this lab, but don't count on this in the future. Also, if you didn't ask for an extension, but you really would wanted to have one, I'm being very lenient for this lab. So just tell us which commit you want us to grade, and as long as that's not 222 in the future, so something around end of the day today would still be fine. Just let me know, I will mark that. But don't count on this as a rule. We have a deadline, Thursday, 10 p.m. That's when we expect you to commit. We expect you to check that you committed the right thing. It's easy. You just go on the website for Git and see that, yep, the commit that you have is exactly what is there. And of course, start early so that when you run into problems with your setup, you have time to resolve them and not, start asking questions late Thursday night when they're unlikely to be answered. Okay. So let's see, somebody is typing. Let's see if there's a question. There's a questions with CampusWire that people have experienced. Just let me know and we'll see what we can do. You can complain to CampusWire if it doesn't connect. You can complain to me. I'll complain to them. If we see that there is a big outage, we'll try and figure out what to do. I mean, at the very least, we can extend the deadline to make sure that that's not part of it. I haven't had big issues with connections. Usually it just works. But, if it's the experience of many people in the class, just let us know and we'll see what we can do. Okay, so more people are typing, maybe to tell me that they also have. Yeah, the iOS app of CampusWire is unfortunately very flaky. I'm told the Android app is even worse. But they do work well enough so that I can see your questions and I can answer if I need to from the phone. The web version is much more stable. Usually, if it's a bigger thing that I need to answer, I just go to the web version. So yeah, it's don't rely on an iOS app only. Definitely use the web version. Okay, so let's get into the lecture. So let's see, I think we have slides for everything. So let's just go through the slides. This is what we're going to cover today. There's quite a lot of concepts. It's a packed lecture. So let's move on. Right. Before we go, just a reminder where you can get help. So first, there is the lab sessions Tuesday, Wednesday, and Thursday. Do use them. We have TAs there. Will involve more TAs if needed. So far, it looked like the TA is not overwhelmed. It says after class, after Monday class, you can ask me questions. After Friday class, I do have a meeting, so maybe I won't answer immediately. But like if you ask questions right after class, I'm still in the class mode and will answer them quickly. CampusWire, as much as possible, ask questions in public. If you worried about that the question is maybe not very well formed, then ask it anonymously. The only time ask a private question if you have code that you want to share, that's your code. And even then, you can ask a question through the class feed. but just mark it that it's only visible to TAs and instructor. And this way, it's visible to all of the TAs and me, and we can answer it together. If only rarely should you use DM, me, or a TA for a question, because yeah, there is a way to do it so that all TAs see it at once. If you need to talk to me, you can always ask, and we'll set up a Zoom session. I've done it with a few people who had special issues to resolve. And then there is this last part, which maybe you haven't noticed. There is a concept of a peer mentor. I know there were several people asking, perhaps there are some volunteers to be peer mentors. If you want to find a peer mentor, post on Campus Wire saying that you're looking for somebody. And if you want to be peer mentor, maybe DM me so that I'll know how many people like this are. Okay, so if you look at the outline, it explains what a peer mentor is. It's somebody who helps another student, don't solve an assignment for them, but helps them sort of more than just talking. And then the deal is that the mentee will get a cap on their maximum grade, so they'll get up to 85, not 100, and a mentor can get bonus points for being helpful. Okay, so what have we learned so far? Just a reminder. So this is what you would expect to see on the midterm, just in case if you're getting lost in all of the course structure. We learned about derivations and grammars, how to go from a string to a derivation, how to interpret a grammar. We're going to do more of this today. So if you don't feel comfortable with this yet, you should be after this lecture. We learned about how to turn a grammar into a parser, into both a recognizer and a parser. We've done this in lab 1 for the W language. We're going to do it in lab 3 for the more complicated F language. And so hopefully after this, you'll be expert in recursive descent parsing. We've learned about object diagrams. I'm assuming you use them in order to understand the code that's given to you. We're going to use them today to understand even more code in this lab. This is something that I expect you to be able to draw and use to gain your understanding about how the program executes. And of course, on Monday, we looked at finite automata, their runs, their executions. And so all of that is would appear on the midterm. Now, in terms of our programming learning progression, so let's focus on lab 3. So in terms of programming, what this lab does, it reinforces all the lessons from lab 1 and 2. So using, well, anyways, it's listed in here. And now the new thing that we're going to learn in lab 3 from a programming learning progression perspective is polymorphism. And we'll see what it is in a bit. And then in terms of testing, we'll look at what kind of other comparison methods we can have for testing other than pure equality and why this may be needed. We're going to look at isomorphic and equivalent. Okay, so let's start first with what's the core task for this lab. The core task is to write or to extend our compiler to support the language called F. F stands for formula. So it's a subset of VHDL that basically allows you to represent formulas and assign them to latches, so to registers. The language looks as you see here. So let me pick a color. So this is how the language looks like. You have a register on the left-hand side, so X, Y, Z in this case. You have an assignment symbol, which in this language, as in VHDL, is this kind of funny assignment arrow as opposed to equality. And then on the right-hand side, you have a formula. And this could be a Boolean formula that has ands and ors, negations, and operators like this. Formulas can be nested, right? So we can combine an or and an and. There can be brackets and so on. And then each statement is terminated by a semicolon. So that's roughly the language. We will see a grammar for it, so we'll make it very precise what the language is, but hopefully the picture makes it clear enough. And so the first question that we have, since we already know about regular languages, and we know that we can write a recognizer by writing, say, regular expression, a question is, well, is this language regular? Can we use the same techniques that we used so far? And you don't necessarily know how to answer this right now. You don't have the tools. We will learn some of those tools. But here the answer is that the language is not regular. And one of the things, the way we can see it, is that in this language, we need to know that every parenthesis, every open parenthesis is matched by a close parenthesis. So whenever we need to recognize whether some sequence of characters is in this language, if the sequence has brackets, we need to know that open brackets match close brackets, which means that as part of our recognizing, we need to basically know whether the language A and Bn, where A is an open bracket and B is a closed bracket, whether sort of that fits into that language. And that immediately tells us that this is not regular. We know that this kind of things we cannot recognize by a finite automaton. Basically, it means that in order to know that every open bracket has a corresponding closed bracket, as we go left to right, we need to count how many brackets we have on the left. And then as we continue, we have to decrease this count every time we see a closing bracket. And for that, we need an arbitrary amount of memory, as much memory as there is open brackets in an input, and a finite automaton cannot do that. So the language is not regular because of the matching parentheses. It's also not regular because in order to interpret it, we really need a parse tree, because we want to know the precedence. We need to express the precedence between different operators. So for example, this expression, A or B and C, we really need to interpret it as a tree like this. That is, that B and C happen together first, and then an OR. It will kind of look like a tree like this. A and B. And operator precedence is something that we cannot express in a regular recognizer. So language is not regular, which means regular expressions will not work. But it doesn't mean that we cannot write a grammar for it. Actually, for this language, we can still write a grammar. So let's see, I just... that is better. Okay, so we still can write a grammar using the same E, B, and F notation. But let's look at how this grammar looks like and what makes it special. So if you remember, a grammar is a sequence of rules. So we have a whole bunch of rules in here. There are terminals and non-terminals. So non-terminals is everything that is in this font. Terminal is everything that is a token. So we have one terminal called ID that represents identifiers. We have terminals that represent particular text. So where a token and the lexeme of the token are exactly the same. So not, and, or, 0 and 1. And then for each non-terminal, we have a rule that tells us how it is expanded, right? And you remember we have derivations where we start from the left, we take something like program, and then we expand it into one or more formulas, and we take a formula, expand it into var and expression, and so on until we get a string in the language. So let's look at what we have in this grammar. So a program is a formula, one or more. And this funny symbol is a traditional notation for end of input or end of file. So a program is basically a whole bunch of formulas followed by an end of input. What is an individual formula? Well, it's a variable, and the variable itself is an ID token, followed by followed by this assignment token, so the less symbol and an equal symbol, followed by an expression, followed by a semicolon token. Now, what is an expression? And so here is something interesting is happening, is we're using the orders in the rules to express operator precedence. Right? So if you'll see, you kind of want to say an expression is just a bunch of things connected with ands and ors. But we don't do this because we want to say that if you look at any expression, then the OR operator is at the top of a tree, which means it happens later than any of the AND operator. And so we express this by using this hierarchy inside of grammar. We say an expression is something connected by OR, and we call this something a term. So an expression is a term followed by an OR and another term, an OR and another term, an OR and another term. But it's also okay if it's just a single term. So an expression is either a term or a bunch of terms connected by an OR. Next, we have a term, and a term itself is because we want negation to have higher precedence than conjunction. So we'll say that a term is a factor, so something else, and possibly a whole bunch of other factors after it connected by an AND. And now a factor is at the bottom of our expression hierarchy. This is kind of the simplest possible expression. And so it is either a variable, a constant, a complex expression wrapped in brackets, or it is a negation applied to the simplest expression, applies to a factor. So with this, we can now start looking at what kind of things, what kind of expressions we can build. So if we start from bottom up, we'll say that, well, an expression can be what? It's either one of those really basic things, a constant to a variable, and then we can take it and apply as many negations to it as we want, and it's still going to be a factor. Right? So for example, if we say not 0, that's fine. That's in the grammar because this is a factor. And then this whole thing is also a factor. And then as we build up, so a term is either a factor, so either whatever we already have, or a whole bunch of other factors connected by an AND. And then an expression itself is a term, which is either a factor, or a conjunction of factors, or a disjunction of terms. I'm going to pause for a second and let you look at this again and see if there's any questions. All right, so there is a question. How does okay, so let's hopefully I can just use the space on the side here, and this will be readable. If not, I'll use a different page. So the question is, what if I have A and B with brackets or B? So the question is, yeah, does this match an expression? So how is this an expression? And so we'll go and we'll look, well, an expression is a term followed by an OR followed by a term. So then it has to be that this is a term. And now I have to make this itself also into a term. So let's see how I can do this. So the term will be at the top. So I'm going to go from the inside out. So let's go and mark this. This is going to be a variable. This is going to be a variable. because it is a variable, it's going to be a factor. And this is a factor. So now I have a term is a factor and a factor. So these three things are a term. And then I have a term, or a term is an expression. Here on the right, I kind of short-circuited this to say this is a term, but if I want to follow the rules, this will be a variable, and then a variable is a factor, and a factor is a term. Okay, so this is my derivation tree. So I can either go this way, where I say an expression is a term connected with ORs, and eventually get down there, or the other way, the way parsing works, where I look at this input and I diagram and classify it according to the rules of a grammar until I get that according to my rules of the grammar, the whole string is an expression. Okay. So there's another question. Let's flip things around. So let's want to wait in case people are still looking at it, because I'm going to erase this and do this again. Okay, so let's erase this and do this again. And I'm going to take some shortcuts, just hopefully that this is clear. So the example is we flip and an or. So it's going to be still a bracket, A, or B, and C. So because there is an and, so the rule that we will want to use is this one. So we'd want to say that this whole expression is a term and therefore an expression. So let's build towards this. So this is a factor. I know that this is a factor because I want to use this rule. And to use this rule, the second thing has to be a factor. So I know it's a variable, and the variable is a factor. So that's why I stopped at a factor, and I don't go higher up. Now, for an A, this is a term, and an OR is an OR. A B is a term. A disjunction of two terms is an expression. An expression in brackets is a factor. And a factor is a term. And a term is an expression. And let's see if I got this right. So I got a factor, and a factor is a term, and a term is an expression. Yep, that looks great. Okay. And I think in the previous example, I ignored the brackets because the expression A and B or C, and the expression A and B brackets or C are equivalent because and has higher precedence. I think in the previous derivation that I've done, I've mistakenly ignored the brackets, and I just had that A and B was a term, but then I had to say, just like here, that this is an expression, and an expression in brackets is a factor. So if you have questions about this, ask on campus wire, and I'll do a clean derivation there. But this one is definitely correct. Okay, so this is our grammar. Now, there's things that are important to note here. We're gonna go over this. We're gonna have theory lectures on grammars and go over that in much more detail. But here is sort of this design pattern, how we build grammars. If we need operator precedence, this guy, then that means that we're gonna have separate rules for different operators. and we're going to nest them so that the thing that has higher precedence, that binds tighter, that's more like multiplication, for example, will be at the bottom of our grammar. And things that bind less tight, things like an addition, will be higher in the grammar. And then whenever we need to say that, well, but then we can have complex expressions inside where simple expressions are, we're going to have some kind of symbol to separate them, like bracket, and we're going to have recursion. That you'll see here, if you're thinking about this in terms of your recursive descent parser, kind of as we go down in the hierarchy here, all of a sudden we get to parse an expression which is higher up. But it's protected by brackets. So we know that we only recurse when this is expected, when we have something that indicates that that's probably what we need to do. Okay, so again, I don't like that it keeps moving the slides, but that's what it does. So the main task for this lab really is to do a recursive descent parser for this language. And we follow exactly the same methodology. That is, every non-terminal becomes a method. Every terminal becomes a call to lexer consume. Whenever we need to look up, we call lexer inspect. Any repetition becomes a loop. We have two kinds of repetition, star and plus. So two kinds of loops. One that iterates at least once and one that potentially doesn't iterate at all. Alternation is an if. As always, first write the recognizer. So something that can say, yes, this is in a language, no, it isn't, and then extend it into a parser. That is something that will also construct the data structure that represents the input. Okay, so in terms of our engineering design, one thing we need to learn is, which technique is applicable. And so we're learning about this recursive descent parsing technique. We know that it works for language W. And from this, we kind of suspect that it's going to work for any regular language. We now have a new language in Lab 3. It's no longer regular. It's a more complicated language. Recursive descent technique still works on it. And so the obvious question to ask is, oh, great. So maybe that's the only technique we need to know. And then it will work for any grammar or other grammars which are more complicated, on which this technique will not work. We're going to look at this. It will work for this language. It's quite easy to see for this particular language just by building a recognizer. And part of the thing that we're going to learn in the theory part of this class is how do we know this, and what makes, how can we look at the language and immediately, maybe with some little bit of reasoning, know whether it is amenable for recursive descent or it isn't. What we're going to look at, and this is sort of foreshadowing the future, is that the languages actually form a hierarchy. So we have the regular languages, which are the languages here at the very bottom of the hierarchy. And there's the languages that can be recognized by the simplest computational machine, which is a finite automaton. On the other hand, there are these other languages here called context sensitive. And these are languages like of open and close parentheses, things like that. This is languages that can be recognized by a push-down automaton, which is a computational machine that is still finite, has finite amount of data, like a finite automaton, but also allows for a stuck. So basically, if you think that it's a programs where recursion is allowed, and if you think, well, can recursion help me? And in fact, if you're looking at a simple model like a finite automaton, recursion does help because you can, for example, every time you see an open bracket, you call a recursive function to process the inside, and then your stack frames keep track of how many open brackets there are, and so that counts how many brackets to close. And then there's this unrestricted, which is any language that for which we can write a recognizer. Basically, when we need not just a push-down automaton, but a Turing machine, a full feature of a modern programming language in order to recognize. So usually we don't want to create languages like this because when we create a language specifically for compiling, we want it to be restrictive enough so that it's easy to parse and rich enough so that it's convenient for users to use. So we really usually stay in context sensitive or close to context sensitive. Regular is just not enough because we usually have operator precedence. And then here in this context sensitive and regular languages, there's two special classes. So one is LL. Let me pick a different color. LL1, which is this box. And this is really the language that we're going to spend sort of most of our time learning. This is a language. This is the kind of languages which is good enough for operator precedence and things like formulas. And then there's a generalization of it called parser expression grammar (SPAG), which we'll also use in lab maybe 5 and 6. Okay, so the language W that we saw before, it was in the intersection of LL1 and regular, so it was both LL1, meaning we can specify it by our EBNF grammar, and we can parse it using recursive descent. And it's also regular, so we could also have used regular expressions. Language F is now part of LL1 still, but it's no longer regular. So what is this LL1 language? Just so that you know the definition. Well, the first L stands for the fact that the parsing goes left to right. So that's a kind of language where if you want to recognize it, you read the input from left to right, and you can eventually figure out whether an input is in the language or not in the language. So you don't need to read the string from the end of it, for example, in order to match it. It's enough to go left to right, and without needing to memorize too much. The second thing is that the second L stands that the language uses the leftmost derivation. What that means is that whenever you look at a rule, which is a sequence of non-terminals and terminals on the right-hand side of a rule, the language always goes down the leftmost non-terminal first. It tries to figure out what it expands to, and only then goes to the next one. So that means whenever you go to the leftmost non-terminal, it has to terminate. It has to resolve in some string. It cannot just loop around. Again, we'll spend quite a lot of time talking about this later. So if you didn't fully get it, don't worry about it. And then this is an important part for us right now. Is that there is a one token look ahead. This is what LL1, this is what the one is for. There is, of course, also LL2 and LL3 and so on with more and more look ahead. One look ahead means that in order to make a decision, we're allowed to look into one symbol ahead in the input, and based on that value of that symbol, decide what to do. So basically, it means that the lexer needs to look at one token ahead and know what it is, so that we can inspect it and then decide how we want to consume it. This is our lexer inspect method. If we have multiple look ahead, then the lexer needs to skip multiple things, and that simply makes it more and more complicated, more and more expensive. If we really want to work with languages that only require one look ahead. And again, we'll spend quite a bit of time looking into when you design a new grammar, where do you make this choice and how do you know that it is one look ahead or whether it will require more? Okay, so let's look back at our language. And so now let's try and understand why it is LL1, and in particular, why it is 1. So the LL part means that whenever we go down the leftmost derivation, so for example, expression, we jump to term, from term, we jump to factor, from factor, we immediately jump to something more basic. So there's never a loop in here. There's never a recursion on the left-hand side. And so that's what makes it LL. And what makes it 1 is that whenever we have choices in the language, so we have a choice, here, we have a choice here, and we have an implicit choice here and here. And so the claim that this is LL1, that every time we have to make a choice, there's only one look ahead that we need in order to know whether, what choice to make. So let's look at the choices here. So, okay. So if we're expecting a constant as the next part that we want to parse, well, it's either a 0 or a 1. So we inspect the lexer, and if a lexer says 0, it's a 0. If a lexer has 1, then it's a 1. And if it's anything else, it's an error. That's it. It cannot be a constant. So we just have two choices, and we can distinguish them by one look ahead. What is right now? What's the next token? For a factor, it's a little bit more complicated. We have 4 cases, but they're all easy to distinguish. So for this case, we just need not to be the next token. So that's when we come to this case. Here, if we see a bracket as the next token, then we know it's this rule. So then we expect an expression right after. If it's an identifier, then we know it is a variable. And if it's a 0 or a 1, we know it's a constant. Okay? Sometimes to figure out what the look ahead is, we need to look at the next rule and actually expand it and see what the look ahead is needed for it. But at the end of the day, in all of those cases, we know we only need a look ahead of one symbol. So it's either a not, in which case it's the first rule, a bracket, then it's a second, an identifier, then it's a third, or 0 or 1, and then it's the last one. Similar for our star rules, we know that we need to go and iterate and consume more things if the next token is an or an and. And that immediately tells us what else we need to expect. So that's a good time to stop for questions. So I'm just going to pause for a second and see if there's a question. Once in a while, my cat comes. And then if I don't pet her, then she starts biting all of my cables. So I really have to pay attention to her too. All right, I don't see any questions. So hopefully this is either clear enough now or will be clearer once you start working with it. So let's go to the next topic. Our next topic is the different trees that we have to deal with in this lab. So the tree of class hierarchy, right? Which class is a subclass of which one? Here we're going to have a classes that represent different types of expressions, and there's going to be a hierarchy of this. There's an abstract syntax tree, which is how we draw abstractly the syntax, where we show which the precedence and which expression is sub-expression of which other expression. And then we have a parse tree, which is essentially the call tree of the parser, right? So it's in a recursive descent, the parse tree corresponds to the calls that the parser will make during parsing. So here's the first one, which is a class hierarchy. So this is what you'll see in the skeleton now for lab 3. We have a new package, which is called AST, for abstract syntax tree. This is a data structure to represent the abstract syntax tree, which will be the output of our parser. And it's going to include all those classes, and the hierarchy indicates what is a subclass of what. So the base of the hierarchy is expression, and has a subclass binary and unary expression. And then binary has two subclasses, and an or, and unary has a not. Okay? The one question that is here on the slide is why one is called binary and one is called unary. Can you guess? I'm looking at the chat, hoping somebody will answer, just to see if you're still here. Right. So the binary and unary stands for how many children we expect. So and expression has 2 children, so it's a binary, or has 2 children, so it's a binary, and negation has 1, so it's a unary. Okay. So number of operands. This is just an example of the source code of those expressions. So I'll just quickly read over it. So we have an expression, which is an abstract class and has an abstract method string operator. An abstract class means that the class is not fully defined. So it defines the methods that an implementation should have, but it doesn't actually define how those methods operate. Right? So it's used to create base classes, but it can never be instantiated. And some people experience that with VS Code during the last lab. We had a base class for a test, and for some reason, VS Code decided to treat it as a test and then complained that it cannot be instantiated because it's an abstract class. Okay? So abstract classes are used to create a hierarchy without providing an actual implementation. Then we have another abstract class, a binary expression that extends expression. Right? It's still abstract because it specializes some part of the behavior, but not all. And we don't expect anybody to ever create a binary expression. They need to specialize it more. They need to make it either an AND or an OR expression. So the way this is designed in here is that a binary expression has two children, left and right. And then it has a method toString that is common to all of the binary expressions that prints the result by printing the left part, well, converting it to a string, not really printing, by converting the left to a string, followed by the actual operator, so it's an AND or an OR in our case, followed by the right part, followed by the string for the right part. And the function operator is still abstract. It was abstract in the base class, and it's not part in here. So this one, so it remains abstract still. So that's what needs to be specialized. And the binary expression also introduces a new abstract method called new binary expression that is used to create binary expressions. Right? And this is a common design pattern where you hide operator creators into usually called a factory, so that there is some control over how the operators are created. Okay? In this case, we're not really using this control yet, but it's still a good design principle that if we want to have control of how expressions are created, we don't allow the users to call constructors directly, rather give them methods to do so. Okay. So we have this. And now we have two specializations. One is AND. It's final because we don't expect it to be extended anymore. We implement the operator to return the string AND with extra spaces around it so that it will print well. And we implement new binary expression by returning the AND expression. So that's what an AND expression, new version of it creates an AND expression. And exactly the same code for OR. So the next, so this was our class hierarchy. Now, what it represents is an abstract syntax tree, which is essentially, the object that are created when the parser runs and creates things. So, for example, for a program like this, the abstract syntax tree looks kind of like this. We're going to have a program, because this whole thing will be a program. The program will contain a single assignment statement, because that's what it is. The assignment has a left-hand side or an output variable called x, and a right-hand side, which is an expression. And in this case, the expression will be an OR expression. It will have left and right fields, which will be variable expressions. And variable expression 1 in some field will remember that it's A, and expression 2 will remember that it's B. So this is what an abstract syntax tree is. It captures the syntax of the expression, but abstractly keeping the hierarchy, but ignoring any of the concrete things like spaces and things like that. And then finally, we have a parse tree, which is same as a derivation, which is the the call tree of the parser, which basically explains how an input fits into a grammar. So here, for example, for this one, if we were to explain, we were to explain why this is part of our language, we'll say, well, it's a program because it is a formula, because it is a variable, and this is because it's an NAD token, and then there is a less than followed by an expression, and an expression, this particular case, this is an expression because it's a term, an or and a term, and A is a term because of this chain, and B is a term is because of this chain. Again, next topic is polymorphism, so I'm going to stop here for a second, see if there's questions. All right, so next topic is polymorphism. So polymorphism is a concept in object-oriented programming, which we'll be using quite a bit in this lab. And this is the idea that every object has two types. It has a static type, which is a type that we know at compile time, and dynamic type, which is an actual type that it has at runtime. Which means if we're making a call on an object, we may not know the function that is being called at compile time, and we'll need to figure it out at runtime. If we have to do this, then this is called a polymorphic call. And we would use polymorphism a lot in order to structure our code nicely, so that we have, well, let's see. So the key intuition here for polymorphic call is that whenever we have a call like this, so we call method m on object x, if the call is polymorphic, that is, if we don't know what is a dynamic type of x, the compiler will figure out at runtime what is the type of x and make an appropriate call. You can think that this is basically looks something like this, that the compiler expands this call into lots of checks to figure out what is a dynamic type of x. In practice, it's implemented using virtual tables, which is a bit more efficient. But this is a good enough picture to have in your mind when trying to understand and use this, which is all that we need for now. And so let's jump immediately into this example and see what's happening in here. So we have a little piece of code that uses our new expression library to construct something with expressions. So let's first look at the code, try and understand what it is doing, and then try and decide what is polymorphic, what is monomorphic. So we first have a local variable called a binary expression. Its value is b, and we populate it by a new end expression. Right? Now, why do we make b be a binary expression rather than an end expression? Well, we just decided to do so. We can because binary expression is a super type of end expression. So this assignment is legal, and so we're doing this. So the reason why we do this probably because we want this code to work also when we replace an end expression by an or expression. The code doesn't really depend on this being an end expression, and we're indicating this by using a super type here. Right? And it has to be binary and not just arbitrary expression, because maybe that's important. Then we create an array of 3 expressions. The array is empty, but it can contain expressions in it. Then we store b inside a0. We store something else inside a1. So up to this point, our array just has an end expression. And maybe the compiler can even statically figure out that even so, we're declaring variables one way, the only value that it can be is an end expression. But now, all of a sudden, we now say, oh, the array, we don't really know. Depending on where you are in an array, it's either an end expression or an or expression. And then we have a call to the b.new binary expression. And it is not clear whether this call is monomorphic or polymorphic, because we need to decide whether, do we know statically which expression will be created, or do we not? Okay. Now this one, the answer here is actually debatable. So I'm going to give you an answer here. In the notes, we say that this is monomorphic because we assume that the compiler is smart enough to figure out that B is only assigned once. B is an AND expression. So a new binary expression is calling the new binary expression of the AND expression. That is, we know that statically, the compiler will take this call and will turn it into a call to, I need to go all the way back. It will turn it to call to this method. Right? And if we know which method will be called statically, then this is monomorphic. Now, as we go further, so now we enter a loop. And now in the loop, we keep reading an element from an array. And now we have to get an operator. And then we have to print it. Okay? And so the question, which is of this mono, which is of this is poly. So before we go, we're going to go into it. What I want to do is I want to draw an object diagram so that we have a clearer understanding of what we're doing. So I'm going to switch to a different screen. If you can, it's convenient for you to have this slide open somewhere, because unfortunately I can't show both a slide and a drawing. I'm going to open it on my screen for me. And I'm going to go and draw an object diagram, just so that we can understand what the code is actually doing. Okay. So if you remember the way we draw the diagrams, we start with a stock frame. There's no static variables in here. So the only thing that we have is a main function. And then it has, well, eventually it will have 3 local variables. There's B, there's an array A, and there's a local variable in the loop E. B is going to point to an AND expression. And that's it. AND expression has no children. We didn't set them, so it has no fields that point anywhere. A will be pointing to an array of expressions. And I'm going to use fields to represent the different what's stored at every index. Then we assign B at A0. So that means we have a link like that. Then we assign a new OR expression at A1. At A1, we have a new OR expression. And then now we make the new binary call for A2. And we know that B points to an AND expression. So we call a new binary on an AND expression. That creates another AND expression. So this is AND expression 2. Okay, let me fix my arrows. This is static variables, so they have to be dashed. Not static, this are local variables, so they have to be dashed. Okay. And now we come to inside the loop. And the first thing we do is we set E to the 0 element of an array. So at the first time, this is what happens. And we happen to be now at PC 11. And the next instruction to be executed is e.operator. So since I don't have the picture of the code, I'm just going to put it in here. And then the next one, so this gets executed and printed. And the next one is e2string. Okay. And so the question is this poly or mono? And the question is this poly or mono? So to answer this question, what we do is we need to look at the type of e and decide whether the function that we call is statically known or whether it's a function that's possibly overridden. And then we need to know the dynamic type of e. We know that the static type of e is expression. This is the type with which it is declared. And of course, we know that the dynamic type of e right now is end expression. So to answer whether this is mono or poly, we need to look at the code and we need to look at this function operator and see whether it is something that can be overridden or not, and whether it is overridden or not. So we're going to go back to our slides and look back at the code. So we are doing now this particular line. That's the one that we were looking at, and we're trying to understand whether it's mono or polymorphic. So we're going to go back to the code and look. So we're calling the operator on an expression. So definitely the call is not monomorphic because we don't know what operator on expression is. It's abstract. So we do need to know what is the actual type right now. So we look at where it is and we see that, well, it's not declared in here. So this function is only declared in here. Okay? And so that means that in order to call the right function, the compiler needs to know, in order to call the right function here, where it's highlighted here, the compiler needs to know what is the dynamic type of e. And that depends on what's in this array. And so the only way for it to figure this out is at runtime to check what it is, which means this call will be polymorphic. So at some runs of this program, in some iterations of a loop, we're going to call an operator of an AND, and in others, we'll call an operator of an OR, and in other, we'll call an operator of this guy, which also happens to be an AND. So this is poly. Now, what about this one? So you may think that, well, if one call on some object is poly, then all calls are poly. But that's not the case. We really need to look again at each function. Where is this function declared, and how many times does it get to be called? So let's look at this again. So we have e2string that is being called. So we'll look at here, and we'll see that the toString method is defined in the binary expression. Right? And so now that's a question. So whether this is poly or mono. If we have more elements in our hierarchy, and maybe they override toString operator, then this call would be a poly call. In this particular case, a compiler will be smart enough to make this into a mono call, because it will say that, well, I know that E is an actual object, right? It cannot be an abstract object. It is whatever its runtime type, it's either an OR expression or an AND expression. If I look at an OR expression, there is no toString method because it's implemented in a superclass. If I look at an AND expression, it's also implemented in a superclass, which means the only function I have to call is this one. And so I can make this call mono. If we wanted to actually be completely sure that this call is mono, if we change this code to be binary expression, then all doubts are gone away. This call is definitely mono, because if E is just a collection of is a binary expression, then the call toString is not overridden in a binary expression. It is just just the call, and so we know what to call directly. Okay, so let me pause here and see if there's any questions. Okay, so let me summarize then the whole thing again to answer this question. So we have two kinds of calls, polymorphic and monomorphic. What's the difference? Monomorphic, we know which function to call at compile time. Polymorphic, at compile time, we cannot figure out which function to call, and the call depends on the dynamic type of an object. Why do we care? Polymorphic calls are more expensive because we can't just call a function. At runtime, we need to do some figuring out. So we need to understand which call is which. That's part of efficiency. Another reason why we care is because when we're trying to understand what happens, it's really important for us to know whenever we make a function call, which function will get called and why. Otherwise, it's just impossible to understand what the program is doing. So that's why we have the two. How do we know that something is mono or poly? Well, first of all, we look whether there's multiple versions of the function in the code that could possibly be at least type compatible with this call. So for example, if I look at this code here, so if I look at this code, I see that operator is defined abstract in the base class. And then I see that there's two kinds of operators overridden, one in an AND expression, one in an OR expression. That already tells me that whenever I have a call to the operator function, unless I statically know what is the type of my object, and it is either an AND or an OR expression, in all other cases, the call will be poly. It will be poly because I will need to know whether I'm calling an operator function in an AND expression or an OR expression. And if I don't know this statically, I'll need to know this dynamically. On the other hand, when we have functions which are not abstract, like a function to string, we just need to see whether it happened to be overridden somewhere. If a function is never overridden, then the call cannot be poly because there's only one version of it. But at the very least, we need to have multiple versions of this function. Okay, so then, there's a question that maybe I've missed. Can the compiler figure out the types of array elements looking at the code? And so this is a very, actually, very complex question because we don't really know, or at least, when we're just talking about an arbitrary compiler, we don't really know what exactly it can figure out. There's certain things which are sort of rule of thumb, what a compiler can do, and the compilers are continuously improved to be able to do more. Usually reasoning about array elements is quite hard, and so that's where a lot of compilers stop. And so if you have an array, then they will not remember which element of an array of which type. But if you just have individual variables, they may figure out. So here, for example, for variable b, a good compiler will know that it's actually an AND expression rather than a binary expression, even so it is declared a binary expression. But for an array a, even a good compiler would not remember what is a0 and what is a1, what is their type. It will just say, oh, it's all expressions, and let's generate a slower code. Then there's a question, what happens about toString method? So toString method is everywhere in Java, and so you don't really need to declare it. It's just automatically in there for lots of objects. And so we just need to override it. And then there's a question, if a compiler did loop unrolling, would everything become mono? And, again, not always. But this is really a reason why compilers do loop unrolling. If you do unroll loops, then certain things become more immediate. And one of the benefits of things becoming more immediate is that you know more about the type. And if you know more about the type, one of the things you can do is convert calls from poly to mono. And that's a big thing in compiler optimizations, like polymorphic calls or virtual calls in C++. They're significantly more expensive than regular calls. And a lot of things that compilers do, still a very active area of research, is how to push this to as far as possible in terms of identifying which function is being called. And if you can reduce it to one function, then turn it into a direct call. Once it's a direct call, it's possible that you can now inline this function. Once you inline this function, this is like loop unrolling. A lot of things become close. And then you may be able to do more and more of such things, more and more optimizations like that. Okay. So this is this. This was polymorphic and monomorphic, and you can expect questions like this, where I'm going to give you code and ask you which is poly, which is mono. If I give you code on a midterm or something like this, I'll do whatever I can to make sure that it's very straightforward, so that I'm not gonna give you hard questions where, depending on how compiler works, it's one or the other. Usually, it's going to be very straightforward. But it's useful to understand that in reality, it's not always. And so that may influence your programming style, because you really want to program in such a way as to have few polymorphic calls. But the polymorphic calls are really useful, like this hierarchy where we can hide which kind of operator it is. So you do want to use them. You just want to be aware that there is a cost. And as much as possible, you want to minimize it. Would polymorphic, so again, in order for something to be polymorphic, a compiler needs to have multiple versions of that function. So if there's only one version, we can assume it's smart enough to optimize and say, yeah, there's many abstract versions of it, but only one implementation. So that's the one I'm going to call. So what is poly and what is mono? In some corner cases, whether a compiler will recognize the call as a mono call or a poly call may depend on the particular compiler. So if with some kind of reasoning you can say, ooh, I can make this call to a single function, then certain compilers can be smart enough and make it into a mono call, and other compilers may say, whatever, I'm not going to optimize, and it may still be polycall. But in other cases, it's very clear. If you have just one function that you're calling, it's always a monocall. And if you have multiple functions, something that's overridden, even potentially, then you could say, well, a stupid compiler will not recognize this and will always use a polycall. All right. So last part of this lecture. So the last part that you need to implement is a comparison for complex structures. So we're going to need to parse these formulas, construct them, and then, of course, for testing, we'll want to compare whether what we parsed looks exactly like what we had. And here the problem is that there may be certain differences in the input and maybe in how we parse and construct the data structures, which are not really meaningful differences in terms of our input. We have normal equality that says two objects have to be equal if they're structurally exactly the same. But this equality will turn, for example, this into not equal, right? Like these two structures, the ones that we have here, A or B and B or A, they are not equal from perspective of equals because they're not exactly the same structure. They are semantically equivalent to us. They represent the same formula, but they're not equal. And so we'll need new concepts other than equality to help us along. Okay? So they're not equal because, like if we print them, for example, the computation will be different. So they're not exactly always the same. So another kind of comparison that we can have, other than equality, It's to say that, well, they're not equal, but there is a mapping from one to another that makes them structurally indistinguishable. And this is what we call isomorphic. So we'll say that two trees or two graphs are isomorphic if you can basically map from one to another. Maybe you're going to change order of children, but other than that, you're not changing much and they represent the same structure. Isomorphism, just like equality, is reflexive, symmetric, and transitive, right? So an object is always isomorphic to itself. If x is isomorphic to y, then y is isomorphic to x. And transitively, if x is isomorphic to y and y is isomorphic to z, then of course x and z are isomorphic as well. The interesting question here is what is the complexity of computing whether two trees, in our case, are isomorphic? And then I think about trees. The only way for trees to be isomorphic is that you start from the root, and all you have to do is pick an order of children so that they match. Right. So the only choice you have is like which way you pick the children, and so the computational complexity of isomorphism is actually polynomial. It's not true of general graphs. Actually, isomorphism is a really interesting theoretical problem from a computational perspective. I'm not sure if this is still current, but for a long time it used to be like in its own isomorphism class, and maybe that's still the case. And it's neither polynomial nor it is NP complete, but somewhere in between there. So it's harder than polynomial, but not as hard as, say, as Boolean satisfiability. What do you mean by similar structures? This is what is in here. So this and this are similar. That is, they are the same except for permutation of children. So here, if I were to draw a tree of one, I have OR A, B, and another one I have OR B, A, and I have a mapping that would tell me, they're exactly the same except this A corresponds to this A and this B corresponds to this B. So we'll say two structures are isomorphic if there is a permutation. So those green arrows that map nodes of one to nodes of the others. That under this permutation, you go from one structure to another. So essentially, as abstract graphs, they are exactly the same. Because in abstract graphs, we don't specify which child is to the left, which child is to the right. This distinction does not matter. Okay. All right, so there is a question on chat. Let me draw it so that we can answer it. So the question, what about this? I have A. Let's see, I have A. And I think it looks like this B, D, C. And I have A, D, B, E. Right? So we would say that these two structures are isomorphic because you just permute the children. Yeah. So in our case, yeah, these two are isomorphic. Okay. So isomorphic means similar. So just under permutation of children, you can go from one structure to another, which also means that in terms of formulas, if I have two formulas which are isomorphic, or two formulas whose abstract syntax trees are isomorphic, then these are exactly the same formulas, right? Because you can turn around arguments of or and and. Now, there's another notion that we would really want, which is even better for formulas, which is equivalent, right? So we would really like to know when we do, say, our testing, that if I have one parser and you have another parser, and we're saying, well, they produce more or less the same thing, mine is maybe fancier. One thing that we would want to do for testing is that the formulas that are produced by one are equivalent to formulas produced by another. Equivalent means that as logical formulas, they mean the same thing. For every input, they produce exactly the same output. They have the same truth tables. In particular, formula A or not A would be equivalent to just a constant one. And so we can define this notion of comparison called equivalence, where we say two formulas are equivalent if they're logically equivalent, if they have the same truth tables. It's easy to show that this is also reflexive, symmetric, and transitive. But the problem is, what is the computational complexity of computing equivalent? And this is where this problem starts, is that to prove that two things equivalent is essentially solving Boolean satisfiability. And we know that Boolean satisfiability is NP complete, which means that even so we don't know whether it's possible to solve it in polynomial time, we don't have any algorithms to do so. And the only algorithms for equivalence that we have are exponential. And the problem with this, it means that if we're going to require equivalence in our tests, well, it's difficult to implement, and computationally it can be way more expensive than what is allowed during testing. So that's why we make a choice and we say, okay, equals is not good, it's too restrictive. Too many things are not equal, but we want them to be treated the same. Isomorphisms over trees is easy to compute, polynomial time, so that's a good one to use. And it removes some of the differences that you can have between different representation of formulas. We really strive for equivalent, but this is just too expensive, at least too expensive in a compiler. We actually will use a SAT solver to test some of your future labs for equivalence, but this would only work for rather small examples. And what's worse, the running time of it is not predictable enough, so that it's a really bad idea to use it in a compiler when people expect fairly constant compilation time. Okay, so this is equivalent. And now this is our final slide. So what you have to do in the lab, if you look at the lab manual, is you need to implement the recursive descent parser, start with a recognizer. You need to implement isomorphism check for the expressions. And of course, you need to implement the pretty printer so that you can have the inverse function for testing. So what to do? So first, for recursive descent, it should be very straightforward to figure out how to write the code. So straightforward that in future labs, we'll see that actually we can generate the code automatically from the grammar itself. So just look at the table, look at what you've done for the W language, and hopefully you'll see that this is really almost mechanical. For the pretty printer, this one is hard to debug because it prints something, and so you have to see how it looks like. So use your eyeballs. Make sure you don't get bugs in pretty printer. If you do, because it's going to be used in testing, it's going to be hard to debug because you may have strange behaviors and you may think my bug is in one place, but it could be in somewhere very different. And then this is an important part. So you're gonna when you're gonna parse expressions, you're gonna need to turn n-ary expressions into binary. So your input may look like this, A or B or C. And for an input like this, you could build two parse trees, right? Because our expressions are binary. One parse tree will look like this. And one parse tree will look like this. Right? Both parse trees are legal. Both ASTs are legal. You can use either one or the other. But in order for us to test, we really want you to use this one. Okay? So don't use this one, use this one. Okay? What that means is that whenever you parse, whenever you have, and you think that you're parsing, you always put the more complicated expression on the left and the simple expression on the right. Okay? Once you start writing the code for the recursive descent parser, you'll try this example, see what AST you happen to get, and if you happen to be getting this one, then you'll know, you can look at your code and see what to change it so that you are getting the right one. I think that's about it. The lab, this one is not super difficult. It shouldn't be more difficult than either lab 1 or lab 2. kind of in the same level of difficulty, but do start early because if you run into problems, sometimes it just takes a while to get over them. And if you're doing it last minute, it may end up being really hard. Okay, I think that's all we have for today. So I'll see you again on Monday, and we're gonna go back to regular expressions and automative. Okay, I don't see any questions, so see you again on Monday.